The enormous explosion is an idea that has influenced our interpretation of the cosmos, outlining the basis of Einstein-based modern cosmology theory, also known as textbook cosmology. The massive explosion was a moment in time when the universe began expanding, indicating the emergence of all matter and life. This occurrence happened approximately 13.8 billion years ago and led to the vast universe we see today. However, recent developments in cosmology suggest that, most likely, the Great Explosion was not the absolute beginning. Instead, there might have been a period preceding the massive blast that was equally crucial in shaping the universe as we know it. This earlier period is known as cosmic inflation. Inflation is perhaps one of the most intriguing aspects of contemporary cosmology. It suggests that before the universe became hot and dense during the massive explosion, it underwent an incredibly rapid and significant growth phase. During this phase, the universe expanded at an astonishing rate. To illustrate how extreme this expansion was, the beginning of the universe, smaller than an atom, would have expanded to a size larger than the entire observable universe in a tiny fraction of a second, around 1/4,000,000th of a second. This inflationary stage didn't last long but played a vital role in shaping the cosmos. When inflation ended, the energy driving the expansion was released into space, warming it and creating the particles of matter that constitute everything we observe in the universe. In many ways, inflation is the precursor to what we call the Great Explosion. Despite the widespread acceptance of the inflation theory in cosmology today, many unresolved questions remain. For example, we are still unsure of what triggered inflation, what caused it to end, or how long it lasted. These are open questions that are important for a deeper understanding of the origins of the universe. Prior to inflation, the universe was in an extraordinarily dense, compact state of matter frequently referred to as a singularity. From this singularity, the beginning of inflation eventually led to the formation of atoms, particles, stars, and planets. The concept of the Great Explosion as the point at which everything began is fascinating, but contemporary cosmology suggests a more intricate picture. Some theories propose that the universe underwent a phase before the massive explosion, and inflation during this phase caused the universe to grow at a remarkable rate. Its size increased nearly 1,000,000,000,000 times in a very short amount of time. This rapid expansion was driven, for a split second, by an odd type of energy that permeated empty space. When inflation ended, the power generated by this growth was transformed into particles, warming the universe and triggering the Great Explosion. This stage of inflation was cold and empty but set the stage for the creation of the universe and matter we observe today. One of the more speculative ideas in modern cosmology is eternal inflation. This theory suggests that inflation did not stop all at once but rather ceased in patches, creating a variety of bubbles, each of which could be a universe of its own. Our universe would be just one of these bubbles. As described by eternal inflation, there could be an infinite number of such universes, each with its own set of physical laws and constants. This is where the idea of the multiverse becomes significant, the notion that our universe could be just one of many, or even an infinite number. If this idea is true, it would help explain why our universe is so perfectly suited for life. In this multiverse scenario, every possible combination of physical laws could exist in different universes, and we happen to live in one where the conditions are ideal for the formation of stars and elements like carbon and oxygen, essential for life to exist. While theories like eternal inflation and the multiverse are speculative, the idea of inflation itself is grounded in observational evidence. Support for inflation comes from the cosmic microwave background radiation, CMB, the first light in the universe. The CMB was emitted about 380,000 years after the enormous explosion when atoms could move freely as the universe had cooled enough. At this point, the universe became transparent, and this light has been traveling through space ever since. By examining the CMB, cosmologists can essentially take a picture of the early universe. This light offers clues about the universe's earliest moments, helping researchers understand what occurred shortly after the Great Explosion. One of the most important discoveries supporting inflation came from the European Space Agency's Planck satellite, which captured detailed images of the CMB. These images show subtle variations in the temperature of the early universe, and these variations match the predictions made by inflationary theory. This concrete evidence supports the idea that inflation is not just theoretical but a key part of how we understand the universe. Understanding the universe's origins, the Great Explosion, and what preceded it requires combining two major theories in modern physics: quantum mechanics, and Einstein's general relativity. General relativity explains the universe's vast structure on a grand scale, including the behavior of galaxies, stars, and planets, whereas quantum theory explains the behavior of particles at the smallest scales. To address fundamental cosmological issues, like what the universe is made of and where it originated, scientists must develop a theory that unifies these two frameworks. This would allow us to comprehend not only the massive explosion but also the circumstances that led to it. One of the most astounding aspects of the universe is its size. The most distant objects we can observe are approximately 47 billion light-years away, meaning the observable universe spans roughly 94 billion light-years across. This may seem odd given that the universe is only 13.8 billion years old. How can the observable universe be larger than the time it would take light to travel across it? The answer lies in the fact that the universe has been expanding over time. As the universe expands, the distance between objects increases, causing distant objects to move further away than light could have traveled in the time since the explosion. Most scientists believe the universe stretches far beyond what we can see. It's possible that the entire universe is infinite in size. The observable universe is essentially the portion we can see, limited by how long light has had to travel since the Great Explosion. This raises the question, is there anything beyond the universe? Most scientists remain uncertain. If the universe is infinite, there is no outside. It would simply continue forever. Even if the universe is finite, it may not make sense to talk about what lies beyond it. This concept, that the universe might be infinite or that there may be countless other universes, touches on the limits of both observation and imagination. It challenges our understanding of reality and raises deep philosophical questions about existence, purpose, and our place in the cosmos. In recent years, advancements in observational technology, such as space-based telescopes and particle accelerators, have brought us closer to answering some of these questions. However, they have also revealed new mysteries. For instance, the discovery of dark matter and dark energy, which together make up about 95% of the universe, has shown us that most of what exists remains invisible and poorly understood. Dark matter appears to hold galaxies together with its gravitational pull, yet it emits no light or energy that we can detect. Dark energy, on the other hand, is believed to be responsible for the accelerated expansion of the universe. Both of these forces play critical roles in cosmological models but remain largely mysterious. Scientists are now using tools such as the James Webb Space Telescope to look deeper into the universe's past, observing the formation of some of the first galaxies. By studying light that has traveled billions of years to reach us, astronomers are essentially looking back in time, gaining clues about the universe's infancy and how structures like stars and galaxies came to be. Meanwhile, in the realm of theoretical physics, researchers are exploring ambitious ideas like string theory and loop quantum gravity in hopes of reconciling quantum mechanics and general relativity. These unified theories could potentially explain everything from black holes and the Big Bang to the nature of space and time itself. Even so, there are fundamental limits to what we might ever know. Some aspects of the universe, like what lies beyond the cosmic horizon or what came before time as we understand it, may always remain beyond the reach of scientific inquiry. Yet, this doesn't diminish the importance of cosmology. On the contrary, it underscores the wonder of exploration. Every new discovery, whether it provides answers or raises more questions, deepens our understanding and appreciation of the universe. At its heart, cosmology is not just a scientific pursuit, it's a profoundly human one. It reflects our innate desire to understand where we come from, why we're here, and what the future might hold. As we continue to push the boundaries of knowledge, we are reminded that we are a small but meaningful part of a vast and magnificent cosmic story, one that is still being written. Beyond would imply something outside of space, which itself is a universe-wide property. So, the idea of something beyond the universe may not have the same physical significance. The origin of the universe is a topic of great study. So too is its ultimate fate. The best current estimate is that the universe will continue to expand forever. This is due to a mysterious phenomenon known as dark energy, which is causing the universe's expansion to accelerate. Before the discovery of dark energy, researchers thought that the expansion of the universe would eventually slow down due to the gravitational pull of matter. This included the possibility that the universe could stop expanding and begin contracting, leading to a big crunch. However, dark energy seems to be tearing the universe apart at an increasingly fast rate. If this acceleration continues, the universe will keep growing forever, eventually getting to the point where galaxies are so far apart that they become isolated from one another. In this scenario, the universe would become cold, dark, and desolate. Stars would drift apart, and matter would eventually decay. This is referred to as the Big Freeze or heat death of the universe. The story of the universe, from the great explosion to its possible end, is one of the most important and complex narratives in science. Despite the fact that we've learned a tremendous amount about the origins of the universe through the theory of inflation and the study of the cosmic microwave background, many questions remain unanswered. What caused inflation to begin and end? What lies beyond the observable universe? Is there a multiverse, and if so, how many other universes exist? While scientists continue to study the universe using advanced technology and theories that unify quantum mechanics with general relativity, we will undoubtedly gain deeper insights into these mysteries. The pursuit of understanding the universe is ongoing, and each discovery brings us one step closer to answering the ultimate questions about our existence. The study of the structure and beginnings of the universe is not only a scientific endeavor, it also raises philosophical questions about the real world and our place in it. One significant part of the universe is dark matter, which is thought to comprise around 27% of the universe's mass-energy content. Unlike normal matter, dark matter doesn't emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter. Understanding dark matter is essential for explaining galaxies' formation and behavior. Ongoing studies and observations have provided insights into dark matter's properties, but its precise nature remains elusive. Several candidates have been proposed, including weakly interacting massive particles, WIMPs, axions, other exotic particles. However, to date, no direct evidence of dark matter particles has been found. The search continues through terrestrial experiments, astrophysical observations, and simulations that model how dark matter affects the large-scale structure of the universe. Another key area of research is dark energy, the mysterious force driving the universe's accelerated expansion. Dark energy is responsible for approximately 68% of the universe's total mass energy content. Its discovery was unexpected and has led to many hypotheses, including the cosmological constant and dynamic fields like quintessence. Understanding dark energy is crucial, as it will determine the ultimate fate of the universe. Researchers are studying its effects on cosmic structures and trying to determine whether it remains constant over time or evolves. In addition to dark matter and dark energy, the study of large-scale structure formation offers profound insights into the universe's history. Observations of the cosmic web, a vast network of galaxies, clusters, and filaments, have revealed how matter clumps together, influenced by gravity, leading to the complex patterns we see today. Simulations run on supercomputers help scientists understand how these structures formed over billions of years and continue to develop. Astrobiology intersects with cosmology as researchers endeavor to understand the circumstances necessary for life beyond Earth. The search for exoplanets, planets orbiting stars outside our solar system, has accelerated with the discovery of thousands in recent years. Some of these exoplanets lie in their stars' habitable zones, where conditions might be suitable for liquid water to exist. By studying these distant worlds, scientists hope to learn more about the potential for life elsewhere in the universe and the factors that make a planet hospitable to life. Finally, the significance of basic physics in cosmology cannot be overstated. The quest for a unified theory that combines general relativity and quantum mechanics continues to challenge physicists. Theories such as string theory and loop quantum gravity aim to bridge these two realms, offering explanations for phenomena like black holes and the early universe. As technology advances, so does our ability to observe and interpret cosmic phenomena. Space telescopes like the James Webb Space Telescope are transforming our understanding of the universe, providing unprecedented detail of cosmic events and distant galaxies. With each groundbreaking observation, we move closer to unraveling the mysteries of the universe's formation, evolution, and ultimate fate. The exploration of the universe is a rich tapestry of scientific and philosophical inquiry. From the fundamental forces that shape large-scale structures to the search for extraterrestrial life, our investigation is a testament to humanity's unyielding and deep curiosity about the cosmos. As we endeavor to respond to these profound questions, we gain a greater appreciation for the vastness and complexity of the universe.